So our next speaker, Brendan Falk, here to speak with us about high-performance fuzzing using vectorized emulation.
Sweet. All right, so this is my first time giving a big talk at a conference, so I'm pretty excited about this. So today, hell yeah, thank you. So today we're going to talk about vectorized emulation, which is a weird concept that I came up with, I don't know, 2 or 3 years ago. Things get kind of weird. So first, a little bit about me. I'm Brandon Falk. That's kind of the easiest part of this talk. And I am pretty much only findable on Twitter. I am on Twitch, I'm on YouTube, but I pretty much post everything on Twitter. So if you want to follow me on Twitter, feel free to follow me. I pretty much have always worked with fuzzing. I dabbled a tiny amount with kind of a little bit of symbolic, and I didn't really get into it too much. So I went really deep into fuzzing, and I've been exploring a bunch of different ways to fuzz. So I've used hypervisors, emulators, modifying kmask, making my own custom things, and as of this year, I actually found a CPU vulnerability, which was really fun. So last month, a couple bugs came out, and I found MLPDS, which I forget what it stands for. And for people who like kind of browsing on laptops and getting ahead in talks, there's a little bit of information up on my blog on vectorized emulation. I go into a little bit more depth on certain things and a little less depth on others. So if you want to go check that out and see what that's like, and just kind of get ahead. So one of the things that we kind of need to get on the same page about is I'm going to talk about these lanes in these vectors as if they're VMs. And I'm going to say VM and guest a lot in this talk, and it doesn't really correlate with the standard hypervisor guest model. So I'm kind of adopting that word to use that to talk about something with its own register and memory state. So in this case, some of the things we'll be talking about is vectors. We'll go a little bit more into what those mean, but it's a register that contains multiple different pieces of data, kind of split up. A lane is a single piece of that data in a vector. The VM and guest we kind of talked about. Parallel is running multiple of these things together or performing an operation on this data in parallel. And then a neighbor, which is kind of a weird concept that we'll hit on later, which is the other lanes of the vector that you're in. So if you are lane 0, it's the other 15 lanes in that vector. So, all right. So what is vectorized emulation? And I don't really know yet either, so hopefully someone can help me out here. But it's effectively emulating multiple VMs using vector instructions on, well, in this case, Intel processors using AVX512. But you could theoretically do it on any processor, maybe even a GPU, where it has these vector registers. So I'm able to gather code coverage. I'm able to gather something called memory coverage, which is tracking the different states of memory, and also register coverage, which is kind of the same thing where you're tracking the different states that registers can be in while running. I have better than ASAN memory protections, which is basically byte-level granularity. Every single byte has its own byte of permissions, so I'm able to have a single byte not be readable in the middle of nowhere. The only reason I say that's better than ASAN is ASAN can't punch a hole in an arbitrary spot, so it's not that much better than ASAN. But the downside of vectorized emulation is since it is emulation in JIT, there's a perf hit, right? Well, it's actually faster than Nivid execution in a lot of situations. So on my single Xeon Phi, which is a fancy machine, but it's only about $2,000, I can run about 2 trillion instructions per second when I'm just doing raw math, when I'm looking at a target that's not accessing a lot of memory. When looking at kind of a standard realistic target that's touching memory and missing caches, it's about 100 billion a second. So to go into this technology, we have to talk a little bit about what vectorization is in the first place, and then we're going to talk about a little bit about snapshot fuzzing, which is kind of how we're able to do this in the first place. Then we'll, of course, talk about vectorized emulation and the results of that. So A little primer on SIMD, or SIMD, or however you want to say it. It is single instruction, multiple data. So this has existed in CPUs for a pretty long time. I'm sure there's some theoretical CPU that could do this in the 60s. But most of the common architectures we know about now, like x86 and ARM and PPC and Alpha, and pretty much every architecture has some vector component to it. And these allow you to use one instruction to perform the same operation or similar operations on multiple inputs, kind of in parallel. And these are the things that you see when you're reversing, and you get into a mem copy and you're like, what are these 20-letter instructions? I have no idea what this is. Usually they just make things a little faster. So you won't really see much use of the vectorized computation unless you're actually doing math-intensive things, but you will see them used for memory operations in the mem class libc functions and the stir functions. So specifically to x86, SIMD came with MMX, which is technically an undefined acronym, but Intel likes undefined behavior. So back in 1997, they kind of introduced, this was back when everything was 32-bit, they introduced 8 new 64-bit registers that you could then split up into kind of subcomponents. You could split it up into one 64-bit register, 2 32, 4 16, or 8-bit registers. And then you can perform operations on these different components of this vector register as if it's or just in one instruction and perform on them all separately. And that really helps kind of speed up, especially back, because that was kind of before graphics cards were big, of doing graphics processing, scaling images, just all sorts of things. So for example, with MMX, here's 4 different add instructions. And they're all packed add instructions. The first one, packed add byte, and that works on 8 different 8-bit lanes. And that goes all the way up through the quad word operations, which works on just 1, the whole 64-bit. So in the case of a packed add word, we'll have this 64-bit register that holds 4 different words. And we'll be able to perform this packed add W, this single instruction, and we'll add these 4 things as they're completely separate. And that's really useful in that we can do bulk kind of vector matricey style math, and we're able to just perform it in parallel and not issue multiple instructions. And kind of as a hit on, the reason this SIMD exists is mostly just for performance. It reduces the amount of instructions you have. It makes the dependencies a little easier to track for the processor because it knows that these are inherently independent pieces of data. And then people who use it, media, rendering, graphics, all these different things. So in modern x86, this has gotten a lot more advanced. You need more bits because you have to win the bit wars. So they added 828-bit registers with SSE back still in the 90s. They added AVX relatively recently, which is 16 256-bit registers. And now, very recently, there's now AVX 512, which has 32 512-bit registers, which comes out to 512 32-bit registers that you can use per thread, per hardware thread. It's pretty crazy how many hardware registers there are. So in kind of a simple comparison of what you would have, you would either have 16 separate adds working on memory because you run out of register space, or a single add. And it ends up being about, in this case, 32 times faster. If you didn't have to touch memory, it's 16 times faster. Who cares? And how do you actually get this SIMD instructions? And you don't JIT them, you don't write emulators that do them. Typically, you write these intrinsics, and you kind of directly write assembly at a high-level language. You could theoretically actually just write it in assembly, but that's pretty rare. But also, nowadays, your compiler will try and emit these for you automatically. So as an example, I just have a little Rust program that adds up a list of 1024 32-bit integers, and we can see that it immediately vectorizes it out, and it's using the whole AVX 512 to perform 16 adds in parallel, and at the very end, it will kind of add up all those neighbors to get you the total sum. And it's actually pretty fascinating technology that they have that can do this. Like, I don't know how we got there. So, to make all of this kind of feasible, we need to talk about snapshot fuzzing, which is effectively the process of taking a snapshot of a program or a system or whatever it is. And usually that just includes the device state, the memory state, and the register state. And if you're looking at a specific application and not a whole system, you can kind of get by with just memory and registers, because you don't really have devices you need to emulate. So as long as you save this somewhere, you're able to reload this information at some point in the future in a new VM or in a new process and kind of make this empty process and start it up from a previous state. And then you can just continue execution, and when a crash happens, you can then reset back to the original state by only resetting the pages that have been modified. And luckily on Intel processors, or many others, they give us a list of all the pages that were modified. So you're able to kind of walk the page table, and even though you're potentially resetting a 16 gig VM, you end up only resetting the 1 meg of memory that was modified during that fuzz case. And that is a huge speed up. So, and that's pretty much the reason that I use snapshot fuzzing. You get to, first of all, skip the application startup times. So when you're looking at a program like Word, something like Office where it takes, I don't know, 10 seconds for it to actually open up, it wouldn't be very reasonable for you to create a file, let's say a docx, click on that file, and then wait 10 seconds every fuzz case. What you could do is potentially take a snapshot right before that input is used, and you get to reset to right before the input is used, and you skip all the splash screen and all the fancy rendering stuff. So snapshot fuzzing also helps when you're looking at targets that are difficult to emulate. So if you're looking at an iPhone, I guess we now kind of have iPhone emulators, which is amazing, but they're pretty hard to emulate on. So if you're able to take a snapshot of the system, you can then copy that and continue executing that in QEMU. You might have to bail out once devices are touched because you don't actually know how to emulate those devices, but as long as you're able to just run your code that's parsing or something like that, you can usually get away with this. Finally, snapshot fuzzing is much more deterministic. It typically should be fully deterministic, but you might have some entropy sneak in. But what's nice is since you're starting from the same state of the program every time, you should know, like, if you pass through the same input, you should get the same result. Maybe you have a bug, I don't know, it varies. And I actually have a whole slide, because determinism means that much to me. Because if you don't have a way of deterministically reproducing your bugs, they're pretty useless. Even if you're an offensive person or a defensive person, a bug that doesn't repro you can't fix. You're going to struggle to actually communicate with the developer what the issue is. You know, sometimes it's easy enough to fix from a just crash stack trace. But typically, it's really nice to be able to go rerun the input that caused a crash through in a debugger, step through, look through all the register states, figure out what actually is happening. Finally, when you have this determinism, you're able to kind of compare what your improvements to your fuzzer actually did. If you're fuzzing on a real, like, live target, it's kind of hard to tell if that byte that you changed in the input actually caused it to hit the new code, or maybe it's just in a different state. Maybe the time's different, maybe something's configured slightly different. So it's easier when you're snapshot fuzzing to kind of do these A/B tests. So, snapshot fuzzing does come with difficulties. It's typically kind of loading up your development and research costs towards the front of your work. And a lot of that is trying to figure out how you're actually going to take a snapshot of the system. And you're not able to really just read the memory of a system in a lot of situations, because if there are timers or interrupts going through, memory could be modified while you're taking the snapshot. So you usually have to get in there, disable interrupts, stop the scheduler, maybe inject some code somewhere where you want to take a snapshot close to where your input's used. And that can make it a little bit more difficult and a lot more research and RE heavy. That being said, I've never really had a problem with doing it. So it seems like there's not a generic way that you can really do it, but there's typically a way specifically for a given target that you're able to kind of rig something up that you can get all this data off in a meaningful way and resume execution in an emulator in some capacity. So a real-world example of snapshot fuzzing is Falkvisor, which is a hypervisor I wrote back in 2013. I fuzzed Word RTF, I fuzzed Defender, I fuzzed, I think, a couple PDF readers. But effectively, for Word, since it had that long startup cost, I had to first figure out where it actually read and used the input file. And I was pretty lucky in that when I looked at this, I found out that that whole startup time, it hadn't even opened the input file yet, which is great. That means I can skip all that. If my input hasn't been read, then I can't influence the program, so I don't care about anything before the input. So I ended up finding that Word kind of has this caching C++ class where they allow you to read files and they cache up the random accesses that are performed in it. And I ended up hooking right after NT-read file in that routine. And once I saw that read come through, I took a snapshot, saved off the whole state, and then I go bring that back in a new VM, load up all the register and memory again, modify only the memory that contains the input, and I resume execution. And by doing this, I was able to fuzz Word at about 4,000 fuzz cases a second, which was a lot for something that traditionally you would maybe, I don't know, get one fuzz case every 15 seconds, because you'd have to wait for it to start up. It's hard to start up multiple word processes because it doesn't scale out linearly with cores. You would have to probably set them up in VMs or somehow configure them to use separate configuration or maybe user accounts or something. All the crashes that I found in this environment were deterministic. So I found some weird bugs that were slightly racy or just slightly strange use after freeze, or even specific ways that things crash, where maybe you have a bug that 1 in a million crashes actually shows up as PC getting corrupted or RIP getting corrupted. And I want to be able to go and reproduce that exactly as it was. I don't want to get a bug that shows up as, holy crap, I have control of PC, and now you have to go back and figure out, oh, well, it just looks like a heap overflow. Like, how did that end up getting PC? So another thing that was really cool is I was able to kind of minimize these automatically. So I could go through, I could take an input. I was actually using 256K inputs, and I was able to minimize them down to usually 20 to 100 bytes in a couple seconds. And that was done by just running the same input through, deleting parts of it, seeing if it crashed in the same way. If it did, you kind of latch that input and then build off that on future iterations. And it works surprisingly well. And when you can do 4,000 fuzz cases a second, you can delete and try deleting things very quickly, and you limit it down pretty fast. So in this case of Word, I found about 30 unique bugs. 10 plus of them were RCE. I actually didn't report them because I was too lazy. And now that I work at Microsoft, I actually reported some of the bugs, and about 30 or 40% from the random dump that I had 5 years ago still existed to this day. So it's not that these are necessarily crappy fuzzing quality bugs. These are actually pretty long-lasting bugs that have survived for years. So after that kind of learning experience with the hypervisor, I started having some issues as I looked at Android, and I started working on targets that weren't on x86. Of course, you could write a hypervisor for ARM64 and kind of do similar things, but I wanted to start heading in the way of emulation. So back, I don't know, 2 years ago, 3 years ago, I had this stupid desire where I wanted to get a Xeon Phi. And I really wanted this mainly because it's a 64-core, 256-thread processor, which I'm not making a mistake there. There are 4 hardware threads, 4 hyperthreads per core. And it makes it for a really interesting piece of hardware that I want to kind of have around, even if it's just to say I have it. So I bought one, and then I felt really guilty about spending, I think it was like $4,000 for this. And I was like, well, I kind of got to make use of this. And the first thought is always just to port Falkvisor to it, because that was my bread and butter for a few years. But Knight's Landing, this Xeon Phi microarchitecture doesn't support VTX. Now some of the Xeon Phis do support it, but not at the time. And so I ended up not being able to use Falk Revisor on this at all. So I started looking into what I could do. And that was basically emulation. And luckily, at this kind of point in time, I was interested in doing more emulation. So I could look at things on ARM and different architectures. So one thing that is nice about the Xeon Phi is it has about 400 gigabytes per second of DDR4 throughput. It has really, really wide, I don't know, more memory lanes. I don't know what the term is. But a traditional kind of like mid-range Xeon processor can maybe do 40 or 50 gigabytes per second. So it was almost 10 times faster in raw memory bandwidth, which makes sense. It's meant for processing scientific data. So I kind of had this idea where I could theoretically lift any instruction. Like if I wanted to lift an add MIPS instruction, maybe I could just generate the AVX512 equivalent of this and do 16 in parallel. So I started thinking through how this could work or how it could not work. And pretty quickly it started kind of looking like it might work. So for example, let's say we wanted to, if we wanted to perform a MIPS32 add instruction, where we're just adding two registers together and we're storing it. So in this case, an add T0, T1, T2, which will add T1 and T2 and store the result into T0. So the first thing I need to think about is, can I represent this instruction using a vector register? And in this case, it's actually really easy. There's a one-to-one translation here. Since MIPS doesn't have flags, I'm able to directly just emit a VP add D and perform 16 adds for 16 separate 32-bit VMs in parallel in one instruction. And in this case, as long as those ZMMs line up with those T registers in MIPS, everything works out, and you can actually just do this. So the question is, okay, and now that this kind of works on arithmetic, which makes sense, will it work for real programs? So I had to kind of think through some of the issues that could come up. So first of all, how do I get all of the same VMs, or all the VMs to execute the same code? If they're executing different instructions, then I'm not able to run them in parallel at all. But luckily, kind of due to what we have with the snapshot fuzzing, they're all starting from a similar point. What happens when they are operating on different register states? So like one VM has a completely different register state than another. What happens on memory accesses? What happens on branches? And hardest, what happens on conditional branches when one VM wants to go do something different than all its neighbors? So getting the same code execution in all the VMs turned out to be pretty simple. Since we already started with snapshot fuzzing, we were able to just load up the same register states. Since everything's already deterministic, all the state has already been computed and it's in the snapshot, theoretically, if you don't modify the input, they will indefinitely do the same thing if you just let them execute. So that was actually pretty simple. You just start them from the same state, and you don't really worry about anything until the user input caused something to behave differently. So even when I first was thinking through this, I was trying to figure out what would happen if this isn't theoretically possible. And at least this is kind of useful for at least skipping the initialization process of a program. So maybe you can't actually run indefinitely in this vectorized magic mode, but you could at least let it quickly go through kind of the startup phases before the user input has caused a divergence in execution. So I was already starting to justify this just a little bit at this point, but barely. So another question that I had was, what do I do with differing register states? And in this case, if you think about it a little bit, it just doesn't really matter. All the SIMD instructions are meant to operate on different data. As long as you're performing the same instruction, it doesn't matter what the actual contents of the registers are. It's just going to do the same thing. So obviously, memory accesses are different there. So memory accesses. What do you do when VMs actually go to access memory? Like, you have to provide this isolated environment. And we effectively implemented a software MMU that allows us to JIT out a page table walk and some way to translate these addresses to some different host address. And this wasn't actually too bad of a problem. It's just a lot more code than I expected. I have to perform permission checks. I have to perform page table walks in parallel if they're accessing different memory. But it wasn't a killer to this idea. So then the final thing is, or not the final, the second to last thing is just standard branches. What do you do in this case? And it's really just like any other JIT. When you get to a branch that you've never seen before, you can't you can't translate that target to your JIT, so you go lift that code, emit the x86 for it, and then you put it in your JIT table. And that's it. So branches are pretty simple when they're not diverging. The hard part is divergent branches. This is what theoretically could just kill this idea of how can you continue executing things in parallel if things aren't doing the same thing. You can't execute an add on 16 VMs if one of the VMs wants to do a subtract. So luckily, very specifically with AVX512, not AVX2 or AVX1, but AVX512 added these magical registers called kmask registers. And kmask registers are 8 new registers that they added. Technically, they're 64 bits wide, but you really only use 8 or 16 bits. And they are labeled K0 through K7. K0 is actually hard-coded to all Fs, but the other 7 remaining registers can be used for general-purpose use. And what you're able to do with these kmask registers, or these mask registers, is you're able to specify to every single vector instruction, or most vector instructions, which lanes you want operations to be performed on. So, and you're able to do this in 2 different modes. You're able to do this in a zeroing mode, where it will zero out the results of things that are masked off, and then kind of in this merging, this preservation mode, where it will maintain and just not perform the operation on those lanes. So for a simple example, if we're performing this add instruction on AVX512 with this kmask of 0110, we'll actually only perform the operations on these, I think they're orange, I'm colorblind, I think the orange lanes here, which are the 2 ones in the center. And effectively, the add will be performed, I don't know, in the processor, it probably performs the add on all of them. But at the end, it ends up zeroing out the 2 lanes that were disabled by that kmask. In the case of merging, it's pretty much the same thing, except the old values just stay there instead of getting zeroed out. So zeroing is a little bit more useful for performance because you can kind of get rid of dependencies, and it makes the processor a little bit faster for those instructions. So these kmasks seems like they could be usable to kind of solve our divergence problem, in that if we made sure that every single vector instruction that we JIT has a kmask associated with it, then we could kind of just mask off bits based on when things go and diverge. So if you have 2 things going to execute a branch, and one wants to go do a subtract and one wants to go do an add, you have to make a decision on which ones you want to follow, the most popular one or whatever, and you mask off the other bit. And now you're able to go perform this add with the subtract path register state masked off, where you're still performing the add on all the lanes, but the results are discarded on the ones that are masked off. And this fundamentally is what makes vectorized emulation possible. Theoretically, you could do this with AVX2, but you would have to manually implement the masking, and it would probably be a 5 to 10x slowdown from this. So it's a pretty remarkable technology, and I'm excited for that to probably influence other vector architectures in the future. So once you've masked off these VMs, you have to kind of make a decision of when do you bring VMs back. And there are a couple ways you can handle that. One, you can just ignore them. When one goes down a divergent path, you can mask it off and just drop it. Or you can mask it off and save that input, and you can use that as a new input in the future, and now you'll be able to follow that path more thoroughly. Or you could end up looking at the graph, find where a post dominator is. Maybe you can find a place where you can merge back up with the neighbors that you lost. There are a bunch of different ways you can handle that merging, and it's like all have trade-offs in their difficulty of implementation and their cost in terms of performance. So after kind of thinking through all these issues, it seemed like there wasn't really anything that would stop this from theoretically working. So I wrote one. So I wrote a vectorized emulator called wafflecone. It's the first generation one. It's 32 bits, uses AVX512. I've actually just started work on a new one that's 64-bit. In fact, the MMU blog that I mentioned kind of at the start is using that new 64-bit architecture. So to make all of this work, I need a couple different components. So in the case of wafflecone, I need a lifter. I need some way of taking target code, whether it's MIPS or x86 or ARM or who cares, and I need to lift this to an IL. I guess you could theoretically go directly from native code directly to JIT, but I think we all know that an IL has a huge advantage such that you can perform these optimization passes and think about this code without just directly translating it. So I wrote a very simple intermediate language. It has like 15 or 20 instructions, and it's just a generic representation of kind of all architectures. And we'll talk a little bit more about the details of that. I have an interpreter that allows me to directly execute this IL kind of in an emulator that allows me to debug my JIT. And then finally, I do have a JIT that allows me to take the Falk IL instructions and kind of template them out to AVX512 instructions. Of course, I need that MMU that we talked about earlier, where I need some way to provide an isolated memory state to all of these different VMs, and specifically in a performant way that can be JIT. I have to walk these page tables in JIT, and that makes it a little bit more difficult because I can't just use hash tables and big data structures. So wafflecone is not the most visually appealing program, mainly because there's no GUI. It's just command line output. So in this case, this is fuzzing the firewall in Windows. So the Windows firewall, I found out very early on when I joined at Microsoft that apparently they do parsing of FTP transactions. And apparently the parsing of FTP transactions was basically done using libc string functions in the kernel. So I ended up finding the bug without this fuzzer first. But once I pointed my fuzzer at it, I was kind of curious to see what it could do. So in this case, we pointed it at this tiny little firewall and ran it with no inputs, no knowledge of what it was. And it was able to pick out crashing inputs by putting this 229 space. There were some other constraints. I think it has to end with a curly brace and a new line or something. And it was able to just generate that, which was really cool. In this case, it had been running for 11 seconds, and we ran 778 million fuzz cases. The yellow number is the FCPS is fuzz cases per second. That's saying it was running at 77 million, and the theoretical number is telling me that it would be running at 615 million if my fuzzer weren't so slow. So it wants to go faster and execute these VMs, but I'm hogging all the CPU time trying to generate inputs. So my fault. So when I kind of have to start to lift up this code, I need to basically get all of this into my IL. And I really suck at using third-party code. It's a personality flaw I have, so I ended up just reading the manuals for multiple architectures. I pretty much always start with MIPS. I love MIPS because it's so easy. You can write a full lifter in a day, and you can be pretty confident that it's probably correct, especially without having flags. So you take a snapshot of a target. You know what it's about to execute because you have the register state and the memory. You go lift that instruction. You convert it into this IL. You basically just spend all the time in the manual figuring out what this instruction is supposed to do, and you implement, hopefully, the same behavior in the IL. And that's really it. It's a bunch of manual work. It's not the most fun thing. So then I have the IL component, the intermediate language that I use. In this case, I called it Falk IL, because I always have to have my name in my projects. And it is not designed to be human readable. It's not binary ninja where it's nice and it reads like C. It's gross. But it's very simple. And that was kind of the point of this design, is that I would be able to rewrite a whole new JIT or an emulator for the entire IL in under a week, or under a day. And what's important about that is that's kind of the only way, realistically, to test if your JIT actually has a better performance property after a change. Is just try it, run it on some real targets, and see if it's faster or better, or it gives you more information. So in this case, it's about 15 or 20 instructions. It's got all your standard arithmetic instructions. It's got your standard bitwise operators. It has one conditional branch and one conditional set of a register, and it's a flagless IL. And being flagless makes it a lot easier because I just ignore flags entirely, and if I have to represent a target like x86 that does have flags, I just allocate internal IL registers to hold those flag values. So it's also a very risky IL, simple, as it is very simple. There are no, it's actually fixed width, so there's no way to perform a 16-bit add. If you want a 16-bit add, do a 32-bit add and mask off the results, or sign extend, or do what you need. It's a load store architecture. There's no way to load memory during an operation. You have to explicitly load and explicitly store. And a bunch of other things kind of in the IL that just make it a little easier to write, work on, and implement these JITs for. So this is kind of an example of what the IL does look like when you visualize it. I have kind of these instruction start markers that indicate where the target instructions lie, and I can use this to kind of, while in the JITted IL, I can translate back to the original target instruction that I'm trying to emulate. Pretty much any IL will have that. It's nothing fancy. So the JIT is actually pretty simple. It's just kind of a template for all of the IL instructions I have. For example, an add IL instruction, all I have is a template of omit a vector add instruction and fill in the registers with register allocation information and just omit it. It gets a little bit more tricky when I have to handle the kmasks, especially as there are some operations that cannot be performed vectorized, and for those instructions I have to actually break out into Scalar traditional x86 and kind of emulate as if a vector instruction is being performed. So I have to honor that kmask even if I'm not doing a vectored instruction. So this is kind of what the JIT looks like. It's basically all gross instructions, and it's just a dense pack of vector instructions, which is what you want. If you're switching between vector and unvectorized code, you actually have a tiny performance penalty to that can add up. So the more vector instructions that you can just do, you kind of keep the processor in that vectorized mode, and it's just chugging along. So not the easiest JIT to read, but it works. And then I have the MMU, which is arguably probably the hardest aspect of this entire project. Not necessarily in that it's difficult, but it's a couple thousand lines of code that you have to get right. And when you do have a bug, it's very difficult to determine what the bug was. It's like, oh, after running a fuzzer for a week and then spending 2 days trying to root cause a bug, it doesn't seem like it's an actual bug, and then you find out like, oh, I'm having off by 1 in my MMU, and everything's invalidated at this point. So to get memory to be fast in this vectorized environment, we have to kind of optimize for the default, the common case. And in this case, the most default situation is that all the VMs are accessing the same memory. The amount of influence that your user input actually has on the program is usually pretty small. So typically the stack accesses are the same, they're accessing the same address, and thus I wanted to optimize for when all the VMs are accessing the same memory. So one way to do this is to interleave all of the guess memory on some boundary. And in this case, in a 32-bit version, I need to interleave them on a 32-bit boundary. And that means in memory, aligned on each 64-byte address, in fact, I have kind of a picture of it, I need to have all of the memory contents for each of the VMs separated by different, in this case, this is quad words or D words. And I will have a permissions 64-bit whole cache line that contains in this case, 64-bit, the 8 different lanes that contain that memory. And then the next 64-byte entry is the contents of that memory. So in this case, we have these permissions, like in this top row, which are 03, 03, 03, and that's saying that all of these bytes are read-write, and that's because I have a byte for every byte of memory of permissions. And then finally, and finally with the contents, it's just they can hold different things. And the reason that I went with this architecture is it allows me to use a single vectored load instruction where I just load an entire 512-bit cache line, and I just load it up from memory when they're accessing an address. And it just works. You load up all the memory for the different guests. It doesn't matter if the guests have different memory or not. And that makes it a lot easier. In the case of they are accessing different memories, say an index came in from the user input, at that point I will need to break it down and perform a page table walk in parallel. And I do have, I'll bring up the URL again, but I have a blog where I kind of talk about the MMU very in depth. It's like a couple pages on just the MMU. So, and then finally what I implemented were some MMU hardening techniques. And this was to make it so I can catch uninitialized memory uses, and I'm able to track just byte level permissions. So to do this, as you saw, I added 1 byte of permissions for every byte of actual memory contents. And all I do is when I go to JIT that something is reading or writing this memory, all I do is check the permissions. So I end up reading both cache lines, and I validate that whatever I'm reading has all the permissions set. I then add an extra bit to this permissions byte, which I call the raw, or the read after write bit. And effectively, if this bit is set on a write, the bit will get copied into the read bit. So you can have memory that technically is readable. For example, if you just hooked malloc and you're returning a new chunk of memory from malloc, you would want to mark all of that memory as write only and then set the read after write bit. And that means that once that memory has been written, then you can read from it without faulting. But until then, it'll allow you to immediately catch if you ever use a single byte out of a buffer that's uninitialized. And it works great. Like, all you have to do is just copy that raw bit every single time a write occurs, and you don't even have to check. You don't have to do it dynamically. It's pretty convenient. So, and then finally, code coverage. I have to gather code coverage because that's what everyone does now. And with a JIT, it's just a joke. Like, you can just count the number of blocks in your JIT, or you can emit code that stores something on branches or stores things on every instruction, and you can just kind of make a list of all the instructions and blocks that were hit. So code coverage is just not really a problem. So this vectorized emulation stuff kind of allows for this new coverage technique that I call differential or divergent coverage. I think I say differential coverage more, but I kind of get confused in my head sometimes. So by running all these VMs in parallel, you typically will have a couple neighbors that are doing the same thing that you're doing. So maybe a couple lanes or VMs ended up getting masked off because they took some branch and we didn't follow that path. But if you have a couple VMs that are still running along with you on certain operations, whether it's a memory read or a register read, you can look to your neighbors and see what they're actually up to. What values and operations are they performing? So in this case, all you really have to do is broadcast one lane to the whole vector register and just perform a compare. So in this case, let's say YMM0 contains 1, 4, and 3, and a 4. And these are different VMs, let's say, performing a register write. And I can broadcast, let's say, the lowest the least significant 4 from this to another register YMM1. And now I have a register containing all 4s. And I can just perform a vector compare, and now I get a mask out of this telling me which VMs are doing the exact same, or have the same value in them. And by doing this, I'm able to determine when VMs have different values in their registers or they're taking different branches. And this allows me to kind of compress down that coverage information. I'm no longer storing the different register states an instruction can have. I'm storing the different register states that the user input influences, because you're only ever storing coverage information on instructions that you have observed that they have different values. And if they have different values and the only thing you're changing is the user input, somehow that user input caused that change to occur. So it kind of gives you this crappy taint tracking. It's a lot different because you don't actually know how the flow occurred, but you do know that your user input did cause a register to be different. So, and with that broadcast and compare instruction, it actually turns out it's really cheap. You just store that wherever you want to perform this operation, where you want to track what has been changed or influenced by the user input, just omit those 1 or 2 instructions, and then you can kind of gate more expensive logic based on that compare. So if they're all looking at the same value, you can just skip reporting this information or doing more intense analysis of what happened in this case. So I'm also able to do this for traditional coverage. It just works in pretty much anything that you want. So in the case of IDA, or kind of visualizing this, the gray color, I think it's gray, once again, colorblind, the gray color shows me which instructions have executed during emulation. The red colors when a register write has been influenced by the user input. And in this case, this is a MIPS load dword instruction, and it's loading into register V1. So by this being highlighted in red, I'm being told that something about the user input causes that V1 register to contain a different value on this instruction. And then we see a branch instruction that's using V1 again, and this one's yellow or green or orange or something. And that is because it's reading a register that's influenced. And since V1 was influenced on the write, of course it's influenced on the read. And what's cool about this is that as a human, I can look at this and I can see, well, there's a bunch of code down this right side that I've never hit before, and it's a user-influenced branch. And that leads me to believe, or to prioritize, this is something that I feel like we probably could find an input that would cause us to go down the other path. So, but now we get to talk kind of about the results. So, unfortunately, I actually haven't used this tool too much. I spent kind of a year working on it and theorizing it. I fuzzed a couple targets. I looked at Windows DHCP. We on the enterprise team, there are a couple people here. We found over 20 unique bugs in Windows DHCP. 6 plus, I think more than that, were RCEs that caused a couple Twitter conversations earlier this year. And with wafflecone, I'm able to find these bugs in a couple minutes. It just instantly runs through almost all the fuzz cases I need to. I found a stupid OpenBSD DHCP bug. It was an out-of-bounds read by 1 that was pretty much unconditional. It was almost always out of bounds, but it didn't really matter. And then the remote blue screen in Windows Firewall. So hopefully in this next year, I'll actually use this tool a little bit more, and I'll write some blogs about using it on real targets, or maybe do a live stream. So what's interesting is with this register and memory coverage, you're able to get really, really cool feedback. So this is the fuzzer that I typically use when I'm fuzzing targets, because I'm really lazy. And it might not look that complex, and that's because it's not. The first thing we do is I grab a random input from the corpus, and the corpus contains previous inputs from seeded crawls of the internet for pings or whatever file format you want, but it also contains things that have been stored based on coverage events. So it contains all those coverage guided inputs. So I pick a random input, I then randomly corrupt some of the bytes in it, and that's it. That's the magical fuzzer. And I pointed this at http.sys in the Windows kernel. And this is what I got after about 10 seconds of fuzzing, is I started getting strings like https:// I got an http/1.1. And while this looks like garbage, you have to remember that this was found without knowing that it is an HTTP parser. I didn't tell it to look for these strings. I didn't seed it with this information. It started with an empty corpus with completely nulled out inputs, and I randomly flip a couple bytes each fuzz case, and I was able to track through coverage and registry coverage specifically different states of the program. And I would find interesting inputs, and I would say, this register I've never seen modified by the user input. Now I've observed that, we save that input, and that allows us to explore kind of more and more state space of the program. This is probably one of my favorite photos I think I've ever created, and it looks really boring, but it's a good feeling. So finally, to kind of stress test this coverage and to write a unit test for this fuzzing environment, I wrote a tool called Hellscape, and I think I actually talked with Richard Johnson about this on Twitter, and I ended up open sourcing it. And effectively, it's just a small little program that's written all in assembly, and it has a couple different bugs. It has bugs that could be found with standard code coverage, where it's every single branch for each byte comparison. It has mem compares that are used multiple times, so you need to source them differently based on where they get called from. It has bulk operations where you're performing a mem compare, but it's working on quad words rather than individual bytes. And wafflecone is able to find all of these bugs in under a second. And I think the only one that AFL or traditional code coverage would find is the branch per byte comparison. Maybe it would brute force its way through a mem compare after 2 years. But I think this really kind of hammers home, and has at least for me, that register coverage is really important. It's very easy to write buggy code or have state machines where the same code is being executed all the time. However, the register state or the program state might influence whether it actually accesses out of bound. But yeah, that's pretty much it for kind of how that works. So we have the end result of all of this, which is the hard question of should you use vectorized emulation? And the answer is probably not. It's a little bit too fast, and I know that sounds stupid, but kind of as I showed on an earlier slide, it wanted to do 600 million fuzz cases a second, and I had a byte flipper, and I couldn't even generate inputs fast enough for it. So good luck providing inputs using a Python fuzzer or any high-level language. You're going to have to get in there and optimize your fuzzers. So it's a lot of work to actually get it to be usable. But mainly, there's probably better things you can be using. Are you using coverage in the first place? Well, start using coverage. Are you auditing code? Are you implementing fuzzers to a specification? Are you implementing fuzzers for vendor-specific parts? Those are pretty much always more worthwhile than getting perf, because this is largely just perf and then a little bit of that solving behavior from that feedback, and it's a lot of work for what you get. So, cool. That's pretty much all I have. So. Sweet. Anyone have any questions?
Hi, great talk. I wonder how many unique bugs you found compared to other tools.
What's that?
How many unique bugs did you find? Like, were your bugs also found by other tools, or were those bugs found only by your tool?
Yeah, so the question is how many unique bugs did I find kind of with this tool? And I'm guessing that the point is like how many more did this find compared to an AFL or any other fuzzer? And I never actually really ran those tests, so I don't really know. I would guess probably half of them are unique, but that's a guess, so I can't give you a concrete number.
How quickly do the VMs diverge? And gave a couple ideas on how to handle once they've diverged, and it looked like you just rescheduled them later. Have you looked at the graph dominant stuff to combine them?
Yeah, so the first IL that I had was actually block-based and had no graphs, so I had no way to find dominators and points for them to converge. Now that I have that new IL, I'm going to look at that model. As for the first part of how often do things diverge, it's surprisingly not too often. So I have a number that I call the V factor, the vectorization factor, which 16 means I'm running all the VMs all the time. And typically when fuzzing a real target, it's normally like 8.5, 8.6, which means I'm losing half the VMs to divergence. However, usually I just don't care when divergence happens, because if divergence happened, my user input caused code flow to change, and I don't really care if there's a perf hit to that anymore, because it's just an interesting event that I don't mind if it costs something. So does that answer it?
Yeah.
Sweet. Anyone else?
Hi. You mentioned that a problem that could be encountered is that you can't generate meaningful inputs fast enough for the fuzzer. Is it not tenable to segregate off some of the cores and pin the fuzzing operations to a subset of the cores and use the rest of the machine to generate more inputs, like to converge on some sort of stable state where you're not starving the fuzzer?
Mm.
Or is this still not cool? Is this still not useful enough?
What's that? Sorry?
The question is, could you not fuzz only on some cores and then use the rest of the machine to generate more meaningful inputs so that you're not starving the fuzzing machinery?
So that's kind of a common thing that I've been asked about this, but typically there's just no performance benefit to just running the fuzzers on separate cores. You're better off just having them run the fuzzer and then actually run the VM, because if the fuzzer takes more time, it just dynamically uses more of the time, versus if you actually scheduled out cores, you would have to figure out, okay, approximately I need this many cores. So theoretically, that could be a speed up based on cache behavior. You spend more time doing kind of the same thing on a core rather than switching between fuzzers and VMs. But most VMs or targets that you're looking at, thrash caches so much anyways that it just doesn't matter. But sweet.
You had a number of instruction counts, like you couldn't reach your total number, but you had something like 77 million out of potential 610 million or billion. What are those numbers? Are those IL instructions or actual from the native assembly architecture of whatever you were targeting?
So in this case, the 77 million number was the fuzz cases per second. But in terms of instructions per second, when I talk about that 100 billion number, that is target guessed instructions. So that would be whatever you're lifting.
Cool, thanks.
Sweet. Cool, anyone else? Sweet, I'm technically over my time, so. All right, thanks everyone for coming out. This was awesome.